Okay, so there's multiple ways of showing that a quadrilateral is a parallelogram, okay? One of those ways is to show that both pairs of opposite sides are congruent. That's one of the theorems out of 6.3. And that's what this one's targeting, okay? If this was totally up to you in regards to the way that you determine whether it's a parallelogram or not, I would strongly suggest not using distance formula to do that. But because this is defined as the technique that they want us to use, we have to. But when we're done, I'll show you maybe a quicker way to say, yes, it's a parallelogram. And then maybe that would be a way to at least check to make sure we're on the right pathway here. In order to find whether a quadrilateral is a parallelogram using distances, we need opposite sides to be congruent. So what I'm going to do, I'm just going to draw a rough sketch of a parallelogram. And to be honest, I don't really care where this is in the coordinate plane. I'm just going to call, actually, maybe I should, just in case that they don't, I don't think they would do this in Math Excel. But I don't want to, I believe, I guess what I'm trying to get at is that they have these points being consecutive. So A, and then we'll travel to B, and then to C, and then to D, and not that you actually go from A to C, back to B, and then to D, or anything like that. So I'm not going to be very precise with my location of my points here. But A is at -2, 0. So maybe that's -2, 0. B is at 0, 3. So there's B. C is at 3, 5. So 3, and then 5 is maybe up there. And then D is at 1, 2, maybe there. So when I'm looking at this, A, B, C, down to D, we can see that segment AB is opposite CD, correct? So AB and CD are opposite. So my hope is that once we go through this, if this is going to be a parallelogram, those two numbers need to be the same. And then BC and AD, those numbers need to be the same as well. And we'll be able to say it as a parallelogram. If they're different, then it's not a parallelogram. So in regards to doing this, the distance formula says that you're going to take your x's for your segment, the endpoints, take those x's and subtract them and then square that. Then you're going to do the same thing with your y's. Once you do that, you're then going to add those together and take the square root. So when I'm looking at BC, finding the length of BC, I'm going to use the points B and C. I'm going to subtract their x's. So if I subtract their x's, I get 3. And then I'll square that. Then I'll subtract their y's. And it doesn't matter the order that you subtract. So if you're going to go 3 minus 5 and get -2, or if we're going to go 5 minus 3 and get +2, it doesn't matter because when I square, a -2 and a +2 both become 4 anyways. So it's going to be 9 plus 4, which is root 13. Is that okay? Now what I would do is I would jump straight down to AD and find AD, because some of these questions could be, I find BC to be 13, radical 13. If I find root or AD to be like radical 12, then I automatically know this is not a parallelogram, right? So I'm going to find AD. Obviously in this question you need to type in all the values regardless, but if it's like an open-ended question and it just says yes or no, then that's how I would maybe approach that answer the quickest. So now I'm going to go A and D. So take that point and that point. Subtract x's. So 1 minus -2 is 3. And then 2 minus 0 is 2. So that again is going to give me root 13. So that right away, BC, that segment there, and AD, that segment there, they're congruent. Okay, both root 13. Now I'm going to do the same thing for AB. So again, subtract the x's. So 0 minus negative 2 is 2. And then 3 minus 0 is 3. So it gives me root 13 there. And then I'll do DC. Subtract the x's. 3 minus 1 is 2. Subtract the y's. 5 minus 2 is 3. Again, I get root 13. So because AB and DC are the same length, we can do that. So this would be a parallelogram. Now, because they're all root 13, I can actually put the same amount of marks in all of them, right? Okay, but this would be a parallelogram. We would say yes, because both pairs of opposite sides are shown to be congruent. Does anybody know what we could better classify that as instead of just a parallelogram? It'd be all the sides are the same. Say again? Some squares are this type of shape, but this shape is not always a square. Because a square, I would need to know knowledge about the angles, right? And if I look at those, if I did any semblance of a decent job of putting my points in the right spots, it looks like A and C are not right angles, correct? So I'm going to say this is not a square. But there are shapes in which we don't have right angles, but we still have all the sides the same length. It's a rhombus. Okay. Which is what we're going to get into today and talk about today. Does that help with that question? Not all of these are going to be, I would argue, and we'll see here real quick. They're not all going to be rhombuses or rhombi. There's one, okay? But you see that a lot of the other ones are not those. You guys remember? So I don't know, so simplify your answer. So some of you might have been getting, like when we do this one here, we find AB. As we go through, so we can find AB, 0 minus negative 2 would be 2. Square that. 4 minus 0 is 4. We'll square that. So we get 4 plus 16, which is 20, right? If I type radical 20 in right there, it's going to tell me I'm wrong. It's going to say you need to simplify. Does anybody remember how I simplify radical 20 from Algebra 1? Does anybody know what radical 20 actually is what it really means? All right, let's talk about this. There is a number that is understood right here. Does anybody know what this number right here in this symbol should be? It's not a 1. It's a 2. Okay? It's an understood 2. That's called for a radical. That number is referred to as an index. Okay? Let's talk about what an index is for like a book. What is an index in a book? How do I use that? Okay, so it tells me where to find something, right? If I'm looking in an atlas, I go to an index. What's an atlas? Okay, so it's a book of maps, right? Okay. So if I, let's say, I need to find Columbus, Ohio. I'll go to the index. I'll go to the Ohio portion of the index, and I'll search through there for Columbus, and then it will tell me, like, D3. So then I'll go to the Ohio map in the book, and I'll find the intersection of either the vertical or horizontal line that's called D, and then the vertical or horizontal line that's called 3, and where they intersect should be in the vicinity of Columbus. Does that make sense? So the index told me how to find Columbus, Ohio, right? If I'm in like my stats textbook, and I go to the index in my stats textbook, and I want to find probability, I'm going to look up the word probability in index, and it's going to tell me what page to reference, what page to go to, right? Okay. So an index tells you how to find something. The index here is telling me how to find this 20, okay? A radical is a symbol for another number. It's like pi. Pi is a symbol for another number, right? It's a symbol for 3.14129, whatever it is, okay? This is a symbol for a number that when I multiply it by itself 2 times, the index tells me that 2 times. Does that make sense? I get 20, okay? So, if we were to take our calculator real quick, because it's an irrational number, so we need, I'm not going to teach you the algorithm to do this by hand. That's just going to be way too much time. I don't really think you would learn that in algebra class. So if I take the square root of 20, and there's a lot of different terms that we can use. We call it the square root. A lot of times we just say root 20. Root 20 means the same thing as square root. Or if I say radical 20, that means the same thing as square root of 20. Those are all synonyms for this. But what that means is if I take that number right there and I multiply it by itself 2 times, do I get 20? So that symbol, radical 20, is a symbol for another number, in this case 4.472135955. And that's only the 10 decimal places. That thing should go on forever without repeating, without ending. It's an irrational number, okay? So it goes out for an infinite number of decimal places. If I capture that entire number and multiply that entire number by itself 2 times, I should get 20. Okay, so this is a symbol for that number, okay? Now, our interest is to simplify that because, like other numbers, simplest version is of benefit. So if I say 2/4, isn't it of our benefit a lot of times to rewrite that as 1/2? Okay. Now there will be applications where 2/4 is useful, maybe more useful than 1/2. Maybe if I'm adding fractions, 2/4 might be better than 1/2, depending on what I'm adding it to. Okay. But in other applications, 1/2 is going to be ultimately better than 2/4. So radical 20 is indeed this number here. This number, writing it that way is terrible because it goes on forever and it never ends. So if I want to write it in decimal version, I can't do that, right? I have to stop at some point. And no matter whether I stop at the 10th decimal place, or if I stop at the 1 millionth, or the 100 millionth, or the Google if decimal place, then I still chop that number off and I make it different than radical 20. Does it make sense? Okay. So radical 20 is the exact version. Okay, but we can simplify this. You guys remember taking 20, I'll do it over here, 20, and dividing it down like that. And then because this is prime, I'm going to stop there with that 2. And I do the same thing with 10. And I'm going to stop at that 2. And I'm going to stop at that 5 because they're both prime. Does that make sense? So what that tells me is that 20 is the same thing as 2 times 2 times 5. Do you guys agree with that? These are all prime numbers. Every single number that is composite, 20 is composite, so any number that is not prime, we call composite. Every single non-prime number can be written as a product of all prime numbers. Okay? So if you give me any number we come across, we should be able to break it down to a product of prime numbers. That process is called the prime factorization of 20. Okay? Does that make sense to everybody? Now, there's a couple ways of thinking about this. We can write 20 as, so radical 20 can now be rewritten as radical 4 times 5. Would you guys agree with that? It's 2 times 2, radical 4. Or I guess it'd be radical 2 times radical 2 is radical 4. But all this is happening underneath the radical, so radical 2, radical 2, radical 5. I can actually, and it's because of the laws of exponents that you learned last year, you can actually do that. And what's the square root of 4? It's 2, right? 4 is a perfect square. And then 5 is prime, so it stays radical 5. So that is a better version of radical 20. If I type in 2 square root of 5, do I still get the same 4.472 number? Okay, so that's the process of simplifying. What you guys probably learned doing this last year was that once you break this down in your factor tree, so you got 20, you go 2, 10, 2, and 5, you would circle groups of numbers, pairs of numbers. So I got a pair of 2s here, and one of those comes out in front of your radical, and then anything that is not grouped goes back underneath your radical. So 5 is not grouped in a pair, so it goes back underneath. And if you have multiple groups, then all of them go out in front, and they get multiplied together. If you have multiple things that are not grouped, then they get multiplied together, and they go underneath. So do an example of something like that real quick. Let's say we have 2 times 2 times 2 times 3 times 3 times. All right, so let's take the number 360. If I want you to simplify 360, okay, what are two numbers that divide 360? Or two numbers that multiply together to give me 360? It ends in 0, so that might be an identifier for a couple different options. 180 and 2 is fine. Okay, if you would have said 36 and 10, that's fine. If you would have said 72 and 5, that would work. Okay, but 2 is prime, so I'm going to stop there. What are two numbers that multiply together to give me 180? I heard 90 and 2. I heard 18 and 10. 36 and 5. A lot of different options. Doesn't matter which ones you choose. They will all work. Now, your tree might look different than anybody else's, but I'm going to go 2 and 90. Okay, now just to change things up, you could keep going by 2, right? It's still a 0 here. I'm going to go 9 and 10. You guys agree that? And then a 9 is going to break down to 3 and 3. And the 10 down to 2 and 5, correct? Does that make sense to everybody? Okay. I stop, this is called a factor tree. And all of these things are like branches of the tree. When a branch terminates or stops, it should stop at a prime number. Okay, so this branch stopped at 2, prime. Branch stopped at 2, prime. Goes all the way down, branch stops at 3, it's prime. All of these are prime. Okay, so that means 360 should be the same thing as 2 times 2, that one times that one. I got another 2 down here. I got 2 3s, and I got a 5. If I multiply those numbers together, 2 times 2 times 2 times 3 times 3 times 5, 360. Every single number that is composite should be able to do something like that. Does that make sense? Okay. Now, this 2 times 2, that 2 times 2 is actually a 4, right? Does that make sense? That 3 times 3 is actually a 9, correct? What's 4 times 9? 36. Is 36 a perfect square? Yes. Okay? So what we're really doing here, and I'm going to show you kind of the elementary way of doing this, but basically what we're doing is saying that 36 is the largest perfect square that divides 360. Does that make sense? 360 would be 36 divided by, or 36 times 10, right? Okay. And then the square root of 36 is 6, and the square root of 10 is radical 10. So this should go down to 6 radical 10, but I'll show you the way that you were maybe taught this last year. You put the radical down. Okay, there is a group or a pair of 2s, right? So bring that 2 out in front. Okay, there is a group of 3s. So bring the 3 out in front. And every group that comes out in front gets multiplied together. So what's 2 times 3? 6, right? Let's turn to 6. Okay. Now the numbers that don't have groups, that 2 doesn't have another 2 to pair with, right? This 5 does not have another 5 to pair with. So they stay on the inside and multiply together. What's 2 times 5? 10. Okay? So what we're doing here is ultimately saying that 360 is identical to 36 times 10 underneath the radical. Is that okay with everybody? Which that is, and I'll prove this with some numbers here in a moment, the same as radical 36 times radical 10. But what's radical 36? It's 6. Square root of 36 is 6. Okay, and I show you all of those things here. And the fact that they're equivalent. So if I go square root of 360, we see that that's the same thing as the square root of 36 times 10, which we could then say is the same thing as the square root of 36 times the square root of 10, which then is the same thing as 6 times the square root of 10. Okay, so they're all equivalent formats. That's the best one for us to work with. Okay, so that's what they mean by simplifying. If you guys struggle with simplifying, because that's going to be, and the reason I talk about this is because we're going to move into a section eventually, a chapter, I don't know if it's the next chapter, if it's chapter 7 or chapter 8, I get them confused, in which almost every one of our answers is going to have a radical in it, and they're going to ask you to simplify the radicals. Okay? If you struggle with some of that, kind of knowing that that's down the road, maybe 2-3 weeks from now, if you go to Schoology, go to geometry, let's see here, where did I put it? It should be on each section, but I don't know if that gets you into, I'll do it this way. Let's put under course documents, add a page. I guess I could turn that to a link. But if I click on that page and then click this link here, it'll take you here. We've been here a few times before. If you scroll all the way down to the bottom to this blue box, this blue table, there should be a radicals cell right here. Click on that. And inside this is going to be a bunch of applets that you can work with practicing how to, one, find factors of a number, simplify radicals, but then here is a handful of videos that tell you how to do all the things that we are going to need to be able to do from Algebra 1 inside geometry with radicals. Adding radicals, simplifying radicals, multiplying them, dividing them, subtracting them. Okay? So knowing that that's coming down the line 2, 3, 4 weeks from now, and you know you struggle with radicals, that might be something that you maybe take a look at, hopefully before we get to that point. Okay, maybe spend 5-10 minutes a night on some of this stuff, just rehashing some of that. That was a good question. Any other questions on that homework? Obviously, it'd be nice if, like on homeworks and just in general on everything, tests, quizzes, handwritten, whether online, whatever it may be, that you had the freedom to do however you want to, answer however you want to. You can totally disregard rules of simplification and all that kind of stuff. That would make life a little bit easier, but that's not how it works. Okay, they're going to ask you to simplify. You're going to need that skill. Moving into 6-4. We're going to talk about some special types of parallelograms. Okay? And these are usually referred to as special parallelograms. Okay? And then I think that question that we just did is a good kind of segue into this discussion, because we saw that in our example, all segments were radical 13. So not only was it a parallelogram because both pairs of opposite sides were congruent, but it had an added feature that all sides were congruent. So it's better classified as a rhombus instead of just a parallelogram. So we're going to talk about these three shapes today and what makes them those three shapes. What makes them qualify to be a rectangle? What makes a parallelogram qualify to be a rhombus? And what's it qualify to be a square? So these are a lot of times called special parallelograms. Okay. And we're going to start all of these with the definition. Okay. And then we will work through what the unique properties are for that shape that make it not just a parallelogram, but make it a rectangle shape. So the definition is that it is a quadrilateral with 4 right angles. Okay? And what I would suggest to you is, instead of writing this word quadrilateral, that you write the word parallelogram instead. You'll see it written both ways, but writing it as a parallelogram automatically tells me some facts, 5 facts that we talked about last week, that should exist before I even know the definition of rectangle. It's a parallelogram, so therefore, opposite sides are congruent. Okay? Opposite sides are parallel. Opposite angles are congruent. Diagonals bisect each other. Okay? 360 to total degrees. Those 5 things are now attached to a rectangle because I know it's a parallelogram. Does that make sense? Okay. And we know basically the textbooks or dictionaries or whatever that say a rectangle is a quadrilateral with 4 right angles. That's fine, because if it's a quadrilateral with 4 right angles, what do you know about opposite angles? They're congruent. And in 6th reading, we say if we have both pairs of opposite angles congruent, that quadrilateral classifies as a parallelogram. Okay, so however you write it, whether you say it's a quadrilateral with 4 right angles, or you say it's a parallelogram with 4 right angles, regardless, it's going to be a parallelogram with 4 right angles. Okay, so that's what we get, what we define a rectangle. Does that say anything about side lengths in the definition? No. Okay, it says not a thing about side lengths. Okay, so the only condition I need to make a rectangle is 4 right angles. Okay. And it says, what condition does this satisfy to be classified a parallelogram? It's the idea that opposite angles are congruent. Okay. So here are some properties of a rectangle. I guess there's 6 if we talk about supplementary. I was saying 5, but I forgot the supplementary of consecutive angles. But these, and now I would not write these. Okay, but those 6 things are true for a rectangle. I would not write those because you already knew that. Why did you already know that? Because those are the 6 properties that are true for a parallelogram. And you should know those for a parallelogram. You should have those written down in section 6.2, right? That makes sense? Okay, so every rectangle is a parallelogram. So every rectangle then should take on the characteristics that are true for parallelograms. Opposite sides congruent, opposite sides parallel, opposite angles congruent, diagonals bisect each other, consecutive angles supplementary, total interior angle sum is 360. So those 6 properties are true because a rectangle is a parallelogram. Okay? We have a theorem which is true because of working with triangles inside a rectangle. Okay? But we have a theorem that says the diagonals of a rectangle are congruent. This is a new property that not all parallelograms have. This is a property that is, right now, only going to be true for a rectangle. right, so right here, I have this parallelogram. Okay, just the general parallel, all we know based on the markings. I don't know if you guys can see the markings very well. I don't think I can change their size. All right, so based on the markings, we got opposite sides here parallel and opposite sides here parallel, right? So based off what we know, that's the only information I'm giving you, this is a parallelogram. And now I'm going to tell you that this angle down here is 51 degrees. So is this a rectangle? If that's 51 degrees? No. So if I show you the diagonals, you can see that the blue diagonal is 14.7 and the red one's 9.32, right? Okay. I'm going to show you what happens as I change that angle. Do you see how the 14 number starts to decrease and the other number starts to increase? And once I get that angle to be 90, now what shape do I have? Now I have a rectangle, right? What do you recognize about the diagonal? Diagonals are the same thing. Okay. And that's because what we will find out is through a little bit of work, we could find that the triangle from E to B to D, that triangle right there, would be congruent to this triangle right here. Okay, does everybody see those two triangles? And if those two triangles are congruent, doesn't it mean their hypotenuses or hypotenusi have to be congruent as well? Which is what the diagonals are for that rectangle. Okay, so that is a feature that is true for rectangles, is that the diagonals are congruent. Okay, let's skip this slide for now. Let's go down to a rhombus. Okay, most textbooks are going to say quadrilateral with 4 congruent. If I say, let's just say 50%. 50% of your textbooks are going to say quadrilateral with 4 congruent sides. But let's think about this. If it's got 4 congruent sides, is that set of opposite sides congruent? Is this set of opposite sides congruent? So do we have a situation with both pairs of opposite sides are congruent? In 6.3, we had a theorem that said if both pairs of opposite sides are congruent, then a quadrilateral is a parallelogram. Okay? So this thing's a parallelogram because of that feature. So if you want to, which again I think is probably a good idea, you can interchange those. You can better classify it's a parallelogram with 4 congruent sides. When you're navigating, so sometimes in homework and quizzes, I'll put questions on the quiz that are vocabulary questions from different textbooks. They might verbalize that vocabulary word of a rhombus. They might say it's a quadrilateral with 4 congruent sides. Or they might write it's a parallelogram with 4 congruent sides. Okay? You just got to know that we can. I think writing parallelogram is a better classification. Is it okay with everybody? Okay, so what makes a rhombus special? Well, one special thing is that 4 congruent sides was not a condition that was needed for all parallelograms. And we saw here that when I show side lengths, like that parallelogram there, obviously all 4 sides are not the same. Okay? So having 4 congruent sides is unique to rhombuses, or rhombi. Okay? And these are 6 properties that we know to be true of a rhombus, and I would not write those. Why would I not write those? Because they're the ones for a parallelogram. Because a rhombus is a parallelogram. Okay. But we do have some other things that are true for rhombus. One of them is that the diagonals of a rhombus are perpendicular. The diagonals of a rhombus are perpendicular. And the other theorem is that each diagonal of a rhombus bisects two angles of the rhombus. Something to, when I see, it bugs the crap out of me. I see my daughter brings home homework. Well, she's in kindergarten, but they're like identifying shapes in kindergarten. So she'll have a circle, square, rectangle, that kind of thing. And then she'll have a rhombus. Well, what does that worksheet call a rhombus in kindergarten? Calls a diamond. Okay? Diamond is not our geometric term. Okay, we're going to use rhombus. Okay. Let's kind of take a peek real quick at those features. So we need, see if I can mess, I don't know if this one will let me do it the way I want it. Hey. All right, so I moved things around here. And what did you recognize that all four sides became? All four sides are the same, right? Okay. Now, if that's the case, that should be a rhombus. So then, when I show you the diagonals, okay, it is saying that the red diagonal is 7.38. The blue one is 17.81. Okay? Because it's a parallelogram, those should get bisected, so I should be able to find like E to G by being 7.38 divided by 2. Okay? But what does it look like the angle is here at G? If I show FGD, that angle, 90 degrees. Okay? So the way I adjusted that, the way I took that parallelogram, started moving it and changing it, was I just focused on changing the sides so the sides all became the same length. Okay? So I went from, I don't know if it'll let me go back. Come on. There we go. So I went from there, okay, which was a parallelogram, right? And I just extended this side EB so it became 9.64, which was there. So I did nothing to the diagonals, right? Okay. If I go back to a parallelogram and I show the diagonals and I show that angle right there, that angle in the middle is 51.41 degrees. And they're not perpendicular. So for parallelograms, diagonals are not perpendicular. But for some special parallelograms, I messed up the order. So some special ones, so 9.64. So now it's a rhombus. Now we see the diagonals are indeed perpendicular, right? Okay. It said that the diagonals bisect angles. So if I view, let's just look at this blue. Take this one, that to go away. There we go. If I just look at that blue diagonal, it's going to bisect this angle down here that is 45. So it's half of 45. $22.5. So if I go find an angle from that side and that side, it's kind of how it won't let me move it. There you go. It's showing this angle right here from F to B to E to be 22.5. Does that make sense, everybody? Okay. What's this angle right here going to be? What do you know about opposite angles of a parallelogram? They're the same, right? So that angle right there is the same as that angle right there, correct? So this whole angle over here is 45. Is this diagonal bisecting that angle then? Yeah. Okay. I don't have a measurement up here, but you should know what that angle right there is. How does that angle, how does this blue angle up here relate to this blue angle here? If it's a parallelogram. Not the same. It is bigger in this case, but that's not always going to be the case. They're supplementary. So if this one's 45 degrees, this one's 135, right? And if I take half of 135, which would be, what's half of 135? 67.5. So let's go back. If I ask for that angle right there, is it 67.5? That kind of makes sense to everybody? Okay. If that's 67.5 and this is 22.5, what's 67.5 plus 22.5? It's 90. And if that's 9, if that one there and that one there are 90, and I've got a triangle here, what does that one right there have to be? 90 as well. And there essentially is the proof for why the diagonals are perpendicular, or a proof of why the diagonals are perpendicular. Okay, so now the next shape. Lots of different ways we could define this. It's a quadrilateral with 4 right angles. So it's got 4 right angles. What do you know about opposite angles? They're the same. So if opposite angles are the same, both pairs are the same, the quadrilateral is a parallelogram. Or I could read this a quadrilateral, instead of saying 4 right angles first, I could say 4 congruent sides first. So if it's a quadrilateral with 4 congruent sides, what do you know about both pairs of opposite sides? Both pairs of opposite sides would be congruent. So then it would be a rhombus, which is a parallelogram, right? So quadrilateral again here can be taken out and replaced with parallelogram. Okay? When I say it's got 4 right angles, you know it is now also a rectangle. When I say it's got 4 congruent sides, you now know it also is a rhombus. So a square is a parallelogram that is also a rhombus in a rectangle simultaneously, right? Okay? So a square is going to have all the features that a parallelogram has. It's going to have those 6 things that a parallelogram has. It's going to have the features that a rectangle has. So 4 right angles. Okay? Diagonals are congruent. Those are the features of a rectangle. And it's going to have the features that a rhombus has. So a rhombus has all sides congruent, and that's evident in the definition there. But it also has diagonals that are perpendicular to one another and diagonals that bisect opposite angles. Okay? So the way I remember things, okay, because a square is going to have what? 6, 7, 8, 9, 10, 11 to 12 properties. Okay? A rhombus is going to have anywhere between like 8 or 9 properties. A parallelogram obviously has 6. Rectangle is going to have 8. I don't want to remember each one of those properties for all of those, right? It's a lot of things to memorize. And there's a lot of them that are redundant. Okay? So what I try to remember is, let's see here, this flow chart. And actually, I'm just going to write it in here. We're going to start. We've got our polygons. And that is going to go down to quadrilaterals at the moment. Okay, we could have, you don't have to write this, but we could have polygons that are triangles. You know, polygons that basically triangles, quadrilaterals, and then we could have like branches for a pentagon, a hexagon, so that n-gon branch is actually showing branches for an infinite number of other polygons. But your quadrilaterals can break off into a couple other categories. The number one category we're interested in right now are parallelograms. Eventually, something that will branch off of quadrilaterals will be trapezoids. And another one would be kites. And if it's not any of those three things, then it's just a general quadrilateral. Just four-sided figure that doesn't have any of those figures. Okay? Parallelograms, we have options. A parallelogram, we just said, could be better classified sometimes as a rectangle, right? But a parallelogram could also be a rhombus. But can it be both those things? Can a parallelogram be a rectangle and a rhombus? And that would be a square. So those two kind of come together and make that square location. So the way I view this flow chart is from bottom up. So if they ask me, what are my properties of a square? I'll check mark basically all the properties that a rectangle has and all the properties that a rhombus has. All the properties that a parallelogram has, all the properties that a quadrilateral has, and then all the properties that a polygon has. Okay? So properties of polygon are basically the things that are identified in the definition where it's got like, in this case, 4 sides, it's closed, no curves, every segment intersects 2 other segments, that kind of thing. The properties of quadrilateral, essentially it's got 4 sides. Property of parallelogram, those are the 6 statements that we should know. Okay? Both pairs of opposite sides parallel. Both pairs of opposite sides congruent. Both pairs of opposite angles congruent. Diagonals bisect each other, 360 degrees total, and then consecutive angles are supplementary. Because a square is a parallelogram, those 6 things happen for it. Okay? Because it's a rectangle, you know 4 right angles and diagonals congruent. Okay? Because it's a rhombus, you know 4 congruent sides. Okay? And diagonals perpendicular, diagonals bisect opposite angles. Okay, so when I look at a square, it takes on all the features and properties of all the shapes that are connected to it above. Does that make sense? Okay. If I want to look at a rectangle, okay, is a rectangle going to have 4 congruent sides? No, because a rectangle is not attached to a rhombus, right? Okay. Rectangle is not below the rhombus. Rectangles are going to have the properties that make it special rectangle. So 4 right angles, diagonals that are congruent, and then all the properties that a parallelogram has. Okay. So the question that you always come across, and you've probably heard multiple times, is a square a rectangle, or is a rectangle a square? Which one of those is? Which one do I say yes? Every rectangle is a square. Is that true or false? That's false. Okay. Because if I start with a rectangle, that is not underneath square here, right? Okay. It's not going to have all the features that squares have. So a rectangle is not a square. But is a square a rectangle? Yes. Because to be a square, by definition, you need 4 right angles, 4 congruent sides, right? What do you need to be a rectangle? 4 right angles. So as the definition of a square, which is more detailed than the definition of a rectangle, but does that definition of a square meet all the requirements that exist in the definition of a rectangle? Yes. Okay. Square, 4 congruent sides, 4 right angles. Is a square a rhombus? Yes, because to be a rhombus, all you need by definition is 4 congruent sides, right? So by definition, square has that. Is a rhombus a square? No, because a rhombus, we don't know whether it has 4 right angles or not. By definition, it says that that's not necessary. It just needs 4 congruent sides. Okay? So when I say all squares are rhombuses or rhombi, you say yes. If I say all rhombuses are squares, you would say no. Are some rhombuses squares? Yeah, if indeed that rhombus was a square, right? Does that kind of make sense on how to ask those and answer those questions? Okay. I think that's one of the kind of overarching questions that people come into a class, a geometry, high school geometry class, having heard but get confused with. Every square is a rectangle, but every rectangle is not a square. It gets kind of confusing how we answer that. But if you know the definitions, you should be able to compare the definitions and then answer that question as yes or no. Does that kind of make sense on how we identify what properties these figures have and what makes them special? Okay, but they're all parallelograms. I'll open up 6-4.